Hello everyone. So, I have been showing you this picture in the last class. We closed here IR source, I have a beam splitter, I have a moving mirror, I have a fixed mirror, beam splitter splits into two and then fixed mirror reflects, the moving mirror also reflects, all the reflected radiation is passing through the sample and goes to the detector, whatever is the remaining, that is unabsorbed IR. So, the arrangement is something like this. Okay. So, the whole instrument, that is FTIR instrument arrangement is like this. I have an IR source here, okay, and I have a laser here that also passes through. Laser is only a reference beam to standardize the IR. Okay. So, that also passes through and the beam splitter is here, moving mirror this way, fixed mirror, and then this is known as interferometer. Okay. And then they both are combined and I have a mirror here again, maybe concave mirror, and then it comes down like this and then one more mirror, and then here, and then out. This is the sample compartment. There is some gas coming in and gas going out, okay. And the IR detector is here, and this is a computer that controls everything, that is movement of the moving mirror and then laser control and then reference control and then sample collection of the data and all that, okay. And it produces a IR spectrum here. So, non-interferometric IR spectroscopy, this is the typical optical arrangement, okay. I have IR source here and then adjustable aperture, basically a slit, and then a sampling accessory. I have a mirror and this is the grating. This is non FTIR. So, grating is here and all the radiation from the grating is collected onto the mirror and it is focused, and then IR FPA detector is here, and after the detector I have a processor and a display device, that is a monitor essentially. Okay. So, the previous one is FTIR and this one is normal IR. Okay. So, instead of using a monochromator, the IR radiation after the passage through a sample can be analyzed by means of a scanning Michelson interferometer. This is a sort of again second year PU physics material, that is interferometer is taught around that level. Basically, it consists of a fixed mirror, moving mirror, beam splitter, etc. So, radiation from the infrared source is collimated by a mirror. This I already told you. I am only putting it here for the record, so that you will know exactly what is happening. So, the mirror is split into two beams, one is passed through fixed mirror, other is through moving mirror. After reflection, the two beams are recombined and they interact at any particular wavelength constructively or destructively depending upon the difference in the optical path. Now, this optical path is introduced because of the moving mirror. Okay. So, the intensity of the emerging radiation modulates in a sinusoidal manner, that is in a repetitive manner. In the case of broadband infrared source, the emerging beam is a complex mixture of modulation frequencies, all of it slightly differing slightly because of the moving mirror. Everything is focused onto the IR. So, this passes through the sample compartment and then on to the detector. So, the detector signal is sampled at very precise intervals during the mirror scan. When the mirror is moving, okay, at that time a very precise movement of the mirror of the order of about maybe 0.01 millimeter is scanned like that. So, both the sampling rate and the mirror velocity are controlled by a reference signal from the detector, that is the laser pointer I had laser light that I had shown in the second picture. So, that is produced by the modulation of the beam from a helium neon laser. It is a helium neon laser. So, the resulting signal is known as interferogram. So, what is the interferogram? It is the total radiation coming out from the infrared source after it passes through the sample. Every information, all the wavelengths, differing only slightly by a little bit of moving mirror changes. So, it contains all the information required to reconstruct the spectrum using a mathematical process known as Fourier transformation. Fourier transformation, it is a very well known mechanical this thing. I am not going into details of what is a Fourier transform and what is a Fourier equation, etc. They are all taught at BSc level. Fourier equation is equation is basically an infinite series, and the equation I will actual equation I can present it to you in the next class, but basically it is a non-ending series, continuous infinite series. Okay, 1 plus x bar bar 1 over divided by 1 factor, then x square by 2 factorial, then x cube by 3 factorial, something like that, it keeps on going. I may be having it here in my slides, but let me show it in the next slide exactly what it is. Okay. Now, assume that basically what we are having is just like an infinite Fourier mathematical expression which contains all the related numbers. I have all the related numbers of an electromagnetic radiation from IR, okay, coming through the mirror. So, it is something equivalent to FTIR, Fourier transform equation. So, what are the advantages of FTIR over the normal filter photometer or grating photometer? I have listed them here, and you can see there is only one moving part that is involved, which is mounted on a frictionless bearing, air bearing. For example, I am going back again a little bit. This moving mirror is mounted on a frictionless bearing. That means the movement of this mirror is very smooth because it is controlled only by air movement, air bearings, and it is uniform, it is reproducible, etc., etc. That means the movement of the mirror are exactly controlled every time you operate an instrument. Okay. So, that is number 1. Number 2, slits and filters are not needed in FTIR, because I do not have to sample a small portion of the electromagnetic radiation corresponding to near IR, far IR, nothing like that. Whatever infrared radiation the source throws, I am collecting everything. So, I do not need slits, I do not need filters. Now, what does it mean? That means no energy is lost, the quality of the spectrum is not lost, because the light intensity falling on the sample and on the detector is essentially same throughout the wavelength range. Okay. That is second advantage. Third advantage is near absolute accurate frequency, better than 0.01 centimeters inverse. because they are all frictionless air bearing, controlled by laser, and also it is controlled by many microprocessor. Okay. So, what happens is, if this kind of accuracy is available, the next advantage is the signal to noise ratio as in a dispersive spectrometer obtained in a fraction of time, the same ratio of the signal to noise. You know what is signal? You know what is noise? You do not know. I have to explain to you. So, the peak in an IR is known as signal. The intensity of the peak below its base is known as noise. Okay. So, basically peak contains noise plus signal. So, for proper measurement, noise should be as less as possible. The noise comes from electrical components. Okay. It is a continuous disturbance of the signal, continuous but fixed. So, that is noise. I have to talk to you about noise, electrical noise in an instrument separately on a separate instrumentation, that I have already taught in atomic absorption spectrometry and spectrophotometry. I am not going into details of that, because I assume that you know about it, or you can go through them for in the same NPTEL program. So, the signal to noise ratio should be as high as possible. That means, noise should be as low as possible, signal should be as high as possible. This is obtained in a small fraction of a time. That means, the noise does not vary much, it is already obtained and already subtracted and taken care of, factored. So, it saves time, because if I can move the mirror number of times, here I have written 32 scans, it saves time per minute. Within 1 minute I am getting all the information, instead of if I move the spectrometer 0.01 centimeter per movement from 4000 to 200, how much time is required? You can calculate per second 0.01, 4000, and then minus 4000 minus 0.01, that is the next second, 4000 minus 0.02, next second, like that. But here it can be done in 1 minute. I can do as many as 32 times scanning. So, I can average it out, and that is another advantage. And then a single beam spectrum is ratioed against stored background in the memory, which gives double beam accuracy. That means, in double beam what happens is, I use only 50% of the radiation passing through the sample, remaining without passing through the sample, so that I can compare the ratio of the sample to that of untreated sample. So, I use only 50% of the sample for the measurement, but in single beam instrument all the radiation is passed through the sample. So, the peak quality would remain much better. So, these are the advantages of FTIR. I think you should remember all this, because I will be asking you questions in the examination about these things if you are taking an examination. Okay. Now, to appreciate how an interferometer works, so far I have told you what is the interferometer and what are the arrangements, etc. But how does it work? I have just given you a small introduction about what is Fourier equation. Now, how a Fourier interferometer works and how it can be related to spectroscopic measurement. I had told you that both of them are somewhat similar, but how similar are they? So, let us see what happens in a single wavelength in the interferometer. Okay. Now, assume that I am passing only one wavelength through the source and onto the beam splitter, and that one single wavelength intensity 50% goes to the fixed mirror, 50% goes to the moving mirror. Now, assume that, and then I want to show you this picture. This is the schematic FTIR diagram. Here is the fixed mirror and here is the moving mirror. The moving mirror starts from this point to this point, okay, and beam splitter is here, sample is here, detector is here, signal is here. Okay. Now, at here I have marked position 0, here it is 0, 1, 2 and 3. Actually, I can mark any number, maybe about 100. I can divide this movement of the mirror, moving mirror, I have divided it here by 4, but I can do it by 100 also. No harm, because it is only a theoretical or hypothetical division of the distance to which the mirror moves from this end to this end. After it reaches here, again it will start moving this end to this end. So, it is continuous movement of the mirror. Okay. So, I have marked them 0, 1, 2 and 3 only for the sake of our discussion. Okay. Now, at position 1, the moving mirror and fixed mirror are equidistant from the beam splitter. So, that means this distance and this distance, actually it is not looking like that in the diagram, but you can assume that this distance between fixed mirror and beam splitter and the moving 0 position and this beam splitter are exactly same. Okay, this is only a schematic diagram, so I have not shown you, but position 1 is that. Position in this situation, both light beams travel the same distance, and when they recombine the beam splitter, they are mutually in phase. That means, there is no difference between the intensity of the radiation between this position and this position, okay? 1 and 2. 2 is always fixed mirror. Okay. So, when they recombine the beam splitter, they are mutually in the phase and there is only a constructive interference. They are in phase. Again basic physics, I will not go into details. So, that means if you remember what I have taught you, you get intense bands of intense radiation, dark spot, bright spot, dark spot, bright spot, like that. So, when they are 0, you get bright spot, and when they are not 0, you get a dark spot. So, this is observed as a maximum signal being passed through to the detector. It is being passed through to the detector, maximum signal. So, any other position apart from this 0 position would be allowing the total radiation passing through the beam splitter would be less than 0 position, except 0, 0 is maximum, and position at 1, 2, 3, this intensity would be much less than the 0 position. That is what we mean. Okay. So, this is observed when it is 0, that means when both the paths are equal, it is observed as a maximum signal. Okay. It is being passed through the detector. So, this signal, let it be unity, that is, it is known as 0 path difference. Path difference between this and this is 0. Okay. Then comes first position. Here I have, let us say I have moved it one wavelength. You remember we have taken only one wavelength. So, lambda by 4 amplitude I am taking. The mirror has moved here, and that means the distance between this and this is increased by this much. Okay. Look at my pointer. So, here 0 is maximum signal, and then it keeps on decreasing. When it comes to lambda by 4, the interference is complete and there is no signal. Okay. Right. So, now as the mirror moves away from 0 position displacement to 1/4, the signal reaches a minimum value or 0, that means it is out of phase. Okay. Here at lambda by 4, this signal reaches minimum. So, here it is no signal. Now, further on it moves, it reaches 1 by 2 lambda OPD. What is OPD? Optical path difference, and it again reaches, slowly it keeps on increasing, it reaches maximum. This is at lambda by 2. Then again it reaches 1 by 4, lambda by 4, it becomes 0, again lambda 3 by 4, again it reaches maximum. So, like that it keeps on moving like this for this wavelength. Now, choose the radiation coming from the IR source contains not just one wavelength, but the number of wavelengths from 4000 to 200 centimeters. Every wavelength goes through this process and all the information is obtained in one shot. Okay. So, if a second wavelength is selected now, a similar waveform is generated, but the maxima and minima are separated by a distance equal to the new wavelength. Okay, 4000, let me say I want to check at 3999, then at 3999 again I get a maximum signal, but the maxima and minima will be slightly lower than 4000. Okay. So, they are separated by distance, it is not the quantity, it is not the magnitude. So, the magnitude will remain the same. Okay. So, in this way what happens is I get a unique cosine wave. For example, this one is cosine wave, cosine 0 is maximum 1, cosine 90 is 0, cosine 180 is 1, cosine 270 is 0, like that. So, this is basically a sine wave or cosine wave, but this is cosine wave. This is high school mathematics. Okay. So, a unique cosine wave is generated for each wavelength. The observed signal at the detector is a summation of all these maxima of the cosine waves, then that is maximum at 0 path difference, that is at position 1, and rapidly decays slowly to 0. So, it decays to a complex overlapped signal which continues to decay with increasing distance to ZPD. When the cosine waves can be resolved, then the contribution from individual wavelength, if I resolve all the 4000 into individual components, okay, then I will get each individual, what I get to know what happens at each individual wavelength, whether it is absorbed or not, how much is absorbed, how much is not absorbed, then I can draw a picture of the spectrum. So, a spectral output of the source I can reconstruct mathematically, and how I convert that mathematically converted spectrum into actual IR spectrum is done by the instrument, microprocessor, etc. There are various aids available. This function is performed mathematically by Fourier transformation technology and for frequency analysis. Why? Because both of them are similar. Now, again I have to take you through a little bit of mathematics, okay. Not very much, not too much, but a little bit, bear with me. So, in mathematical terms, the Fourier relationship is defined as a pair of integrals. The whole Fourier relationship I can define by two integrals. One is the intensity part, another is the source intensity. One is so intensity of the interferogram as a function of retardation. The movement of the mirror is known as retardation, okay. That you should remember. So, the one is intensity of the interferogram as a function of as a movement, lambda by 4, lambda by 2, lambda by 3 by 4, 3 lambda by 4, 3 by 4 lambda, like that. That is I delta, and another is BV. B is the source intensity as a function of the wave number. So, what is that I delta? I delta is, it is the intensity of the interferogram varies from minus infinity to plus infinity. It is a signal, you know, it is an infinite series, and that is given by BV into cosine wave, and the amplitude of the cosine wave is given by 2 pi V into delta D into V, and BV is nothing but I delta. This is, both of them are functions of each other. Now, you can see here I delta is a function of BV and BV is the function of I delta. So, remaining is essentially same. So, but both of them are minus infinity to plus infinity. So, essentially what we are saying? We are saying intensity of the interferogram is almost same as intensity of the source source. So, I get two series of the two functions interdependent upon each other, that is what it means basically. Okay. So, the idealized interferogram, that is one signal, single signal what you get in FTIR is one big burst maximum and then slowly it decomposes into 0. It is like plotting a bell, the sound of a bell, you hit it once and then slowly it goes down to 0. So, like that interferogram also can be plotted like that. An idealized interferogram has a unique center burst corresponding to 0 path difference with a maximum intensity at the center than on either side. Okay. So, as the sample is introduced, the distribution of information changes depending upon the natural line width, what we are every 0.01 centimeter the information changes, and that line width of the infrared spectrum of the sample, and consequently the signal also will change. Okay. So, that will be observed in the wings of the interferogram. The actual infrared spectrum is observed at the wings of the interferogram. Now, I will show you what is, how an interferogram looks. So, somewhere here I have, I have not put it here, but next time I will show you that. It should have been here, yes. I will introduce you to that, but basically I can show you. It will be like this. Something like this. It will not be such a big gap, but it will be something like this. The interferogram, a center burst, and then there is something like this. Though, so up to this it is the interferogram. Okay. So, the idealized interferogram has a unique center burst like what I had shown you here, and then corresponding to ZPD, this I have already covered. Now, you know how an interferogram looks, and the spectral resolution of an IR instrument, we can define it as the ability of the monochromator to separate two spectral features such as peaks or troughs or as the ability to observe the separation of discrete wavelengths. For example, if I have to draw the IR spectrum would be like this now. This is percent transmittance, this is the centimeters inverse, okay. This is the wavelength or centimeters inverse. The two spectrum how good they are separated, that is what it means here. Delta V, the ability to define two cosine waves of different frequencies when they go out of phase and remain in phase at least once, that is delta V is equal to V2 bar minus V1 centimeters inverse, and maximum resolution of a spectra is defined as 1 over lambda delta lambda max, 1 over delta max, where delta max is the distance of the moving mirror. So, once data is obtained at a specific resolution, spectrum of resolution can be artificially generated by using a subset of the data or extrapolation. So, I want you to understand now that what I have obtained is an interferogram. What I have shown you earlier in my drawing is an interferogram. How that interferogram can be divided into small portions, okay, and then converted into spectrum. So, the spectrum can be converted if I use D transformation. Okay. First I have the Fourier transformed spectrum. Now, when I do this D transformation, I get the IR spectrum. So, theoretically the information of FTIR should be collected at infinite retardation. Okay. So, please try to understand now. An infinite retardation means the moving mirror should be moving in very small and infinite speed. Okay. That means from one point to another point it must take infinite time to reach theoretically. But in practice what is required is it is acquired at practical distances. Okay. So, I can say 1 centimeter maximum it can move or 2 centimeters, but if I keep it infinite distance, FTIR spectrum cannot be taken, okay, or it will never end. So, I have certain restrictions, that is it is acquired at practical distances, which results in the truncation of the interferogram. So, now if I have a spectrum like this now, somewhere here I have to cut the rest of the information, even though it may be there, but I am not going to collect this information. Not collected. Same thing is here. That means, I am truncating the Fourier transform from infinite to a particular finite position. Okay. So, this results in the truncation of the information. So, truncated information is only this much. This is truncated information. Okay. So, at some stage I had to cut it off, and hence the separation will be always lower than the predicted value. This is understood now. So, this is known as apodization. So, this truncation is decided by the manufacturer. So, what is required to be done is that the I have to, while doing the FTIR, I must say you stop at this stage of the moving mirror. Do not make it infinite, but stop after 2 minutes or 3 minutes or 5 minutes, like that, collect all the information within that time. So, that is known as truncation on either side, 0 and 1. So, this that is known as apodizing function. It is done mathematically. So, I can give any number, I can write a program, computer program, and say truncation at this level. So, an apodizing function needs to be applied to reduce the effect of premature truncation. So, now you understand, try to understand, whenever I have to do this truncation, part of the information is lost. But so to take care of that, I have to add a little bit of correction. How much is lost? I do not know. So, that function is also decided that I have to add a little bit of the information to reduce the effect of truncation, the premature truncation, that is apodization. So, this acts like a weighting function. So, I need one apodizing function on the higher frequency side, another apodization on the lower frequency side, and then there are two apodizing functions. Apodizing is a separate branch by itself, that is how much to cut, etc. That is two applications are known in the instrumentation world. One is known as Hanning apodization, another is Hap-Genzel apodization. So, these two techniques are used for truncating the Fourier transform signal. So, I am not going into details of this Hanning and Hap-Genzel techniques, but suffice it to say that you can stop the Fourier transform from infinite to a particular size, practical size, and they are known as truncating the FTIR, Fourier transform, and this truncated information needs to be taken care of. So, that acts like a weighting function, and these weighting functions are known as Hanning function or Hap-Genzel. So, this also reduces the noise, and since the noise is always uniformly distributed throughout our interferogram. Okay. So, the signal produced is also a phase dependent phenomena, okay. That is understood now, because I have to cut off the signal, collect all the information, cut the FTIR into specific information, and then optical components can also cause dispersion, that is mirrors, etc., beam splitter, some amount of aberration is always possible. There is nothing like a perfect material in this world. Okay. Detector also can introduce errors. So, etc., all these things can introduce a little bit of phase errors in the final spectrum. So, phase corrections are also normally applied to reduce the photometric errors. So far I have talked to you about FTIR. Okay. Next, in our next class we will start talking about sample handling. So, what I have taught you today essentially is there are three types of instruments: filter photometers, grating photometers, and FTIR. I have taught you the basic arrangement of the optical system in these three systems, and we will continue our discussion in the next class. Thank you very much.